All right then. So we learned some chord properties related to chords. We learned some properties of angles in a segment, angle in a semicircle, and so on and so forth. We then looked at cyclic quadrilaterals, a very important property of cyclic quadrilaterals. And we also looked at a very basic property of a tangent to a circle, which is like the radius at the point of tangency that leads to the radius being perpendicular to the tangent. Now I'm going to discuss a property of circles. I have always been telling you all properties are useful, yes, because whatever we are doing right now are actually useful properties. Otherwise we wouldn't be doing these properties. But then, you know, the fun thing would be when we put together all these properties in a given problem and arrive at a beautiful concoction. So then, if you recall, in one of the earlier sessions, I told you what a secant is. This is a secant to a circle. Say this is a point P anywhere, and I draw a line that intersects the circle at two distinct points, A and B. Then this PAB is said to be a secant to a circle. This is a secant drawn from a point P to the circle. Now, the property that I am going to discuss is the following. So from the point P, how many seconds can you draw to the circle? How many seconds could you draw to the circle? Infinite seconds, right? Infinite seconds could be drawn to the circle. This is one. What's common between all the seconds that you could draw to the circle? That's the property that we will investigate. Let me tell you then. Let me first tell you the property and then go ahead and establish the same. So let's say this is another secant drawn from P to the circle. What we could do is, you know, we might, just to create more room, let me draw them spaced further apart so that we have more working space. Say this is another secant drawn from P to the circle. Call it PCD. PCD, yet another secant drawn to the circle. Now, the property that we will establish is the following. PA into PB, where A and B are points of intersection of the secant with the circle, will be the same for all seconds. That means whether I take PA into PB or I take PC into PD, it's going to have the same value. It's going to have the same value. That means PA into PB will essentially be the same as PC into PD. Will be the same as PC into PD. That's the property that we are looking at. Now, nothing difficult in as far as the property is concerned. We can very easily establish this property. What we do is, let me join A and C and let me join B and D. Let me join B and D. Now, look at this quadrilateral ABDC. What kind of a quadrilateral is ABDC? ABDC, obviously, you know, these points lie on the same circle. So this quadrilateral is cyclic in character. It's a cyclic quadrilateral. Now, a property of cyclic quadrilaterals, opposite angles of a cyclic quadrilateral are supplementary. That means the angle here plus the angle here is 180 degrees. The angle here plus the angle there is 180 degrees. Right? That's a property of cyclic quadrilaterals that we've learned. Now, realize that this angle, if this is alpha, then alpha plus this angle is 180 degrees. Yes or no? Alpha plus this angle is 180 degrees, isn't it? And this angle plus this angle is also 180 degrees. This angle plus this angle is 180 degrees. Why? These are angles in the same straight line, right? Since PCD are collinear points, the angle ACP and the angle ACD is 180 degrees. So if this angle plus this angle is 180 degrees and this angle plus this angle is 180 degrees, that means whether you add this angle to this angle or you add this angle to this angle, it's giving you the same value. That means if this angle is alpha, would you mind believing that this angle will also be alpha? Right. Similarly, if this angle is beta, then this angle beta plus this angle, that's 180 degrees. Opposite angles of a cyclic quadrilateral supplementary. That means now if this angle plus this angle is 180 degrees and if this angle plus this angle, which is also 180 degrees. Why? Because PAB is a straight line. Therefore, this angle plus this angle is 180 degrees, right? So, to this angle, whether I add beta or I add this angle, it's going to give me the same value. That means to this angle, if I add beta, it's giving me 180 degrees. To this angle, I add this angle. That's also giving me 180 degrees. Which means, if this is beta, then this must also be beta. This must also be beta. Now, it's all straightforward. If you've done similar triangles properly in the past, then you would have a hang of it. You would know that it's ordinary stuff. Realize that in triangle PAB, PAC for example, this triangle PAC and triangle PDB. See, look at this triangle PAC and PDB. Look at these two triangles. How difficult is it to establish that these two triangles are similar triangles? Hey, one of the things that you can see is if I compare triangle PAC, this triangle, with this triangle PDB, do you see that this angle is equal to this angle? This angle beta of the smaller triangle is this angle beta of the bigger triangle, and the angle P is common to both the triangles. And the angle P is common to both the triangles, which means the two triangles must be similar. Triangle PAC must be similar to triangle PDB. Very good, very good. And then, if this happens, then proportionality would lead to, that means side opposite to this beta is what? PC. See, if two triangles are similar, their sides must be proportional. So, opposite to this beta is PC. Opposite to this beta of the bigger triangle is PB. So, PC proportional to PB. Alright, look at this angle alpha. For the smaller triangle, the side opposite to alpha of the smaller triangle is PA. The one opposite to alpha of the bigger triangle is PD. And then all that you need to do is to cross multiply and perform the last rights on this. You get PA into PB is PC into PD. PA into PB is PC into PD, which is a property very commonly used and a very effective property. I must tell you that when we solve problems, we are going to use this property time and again. All right. Now, let me also tell you a corollary of this property. Let me tell you a corollary of this property. A corollary of this property. Hey, if I have a point P, this is a secant that any secant that I draw from a point P, PA, PB, right? Now, I could keep drawing seconds. This would be another secant, this would be another secant, and in all these seconds, the points A and B are distinct. However, there is one secant that you could have drawn from P in which A and B A and B become coincident. What secant is that, by the way? Given the notion of tangents that I have taught, you should be able to tell me what secant drawn from P would have A and B degenerate into one. That secant would be actually a special secant. That's going to be a tangent. That's going to be a tangent. This is PT. This is PT. So this is a secant in which A and B coincide, So even though this is C and D, I could have said from the property that we've just proved, PA into PB is PC into PD, is PE into PF, PF, and so on and so forth. In this case, E, F, C, D, A, B, all of them coincide. So it's as if E becomes the same as F, T and T. You would then, as a special case, want to say this is PT into PT. That makes it PT squared. You know, those of you will look at it with skepticism. Therefore, what I'll do is PA into PB equal to PT squared, where T is the point of tangency. I will also establish from independent considerations so that, you know, you are at home with traditional stuff as well. Now, are you fine with this? No issues, right? Okay. Say this is a point P, and I draw a secant PAB and a tangent. Say this is a tangent PT. Then I want to show that PA into PB must be PT squared. All right. Okay. Now, what we do is I join A to T. I join A to T. I join T to B. Right? Now, this angle that the chord AT makes with the tangent at T, that is this angle alpha, will be equal to this angle alpha. Why? Why? This is a chord. The angle made by the chord with the tangent must be equal to angle in the alternate segment. That means this must be alpha, right? All right. This angle is common. I'm trying to compare triangle PTA and triangle PBT. PTA and PBT are the two triangles that I'm trying to compare. Now in the two triangles, this angle P is common to both. See, this angle equal to this angle of the smaller triangle equal to this angle of the bigger triangle, and this angle is common to both the smaller and the bigger triangles, and therefore the third angles must also be equal, because if two angles are equal in a triangle, then the third angles must also be equal. That means, realize that if this angle is beta, then again, what's the third angle of the triangle? What's the third angle of this triangle that would be equal? See, for the bigger triangle, I have confirmed this, I have confirmed this, and therefore, would you not want to say that this third angle of the bigger triangle, must also be equal? This angle must be beta equal to this angle. Yes or no? Yes or no? Yes, of course. Now, all that we need to do is to be able to apply similarity of the two triangles. How do we apply similarity of the two triangles? All that one needs to do then is similarity of the two triangles. Opposite to this beta of the smaller triangle is PT. opposite to this beta of the bigger triangle is PB, equal to, opposite to this angle alpha of the smaller triangle is PA, opposite to this angle alpha of the bigger triangle is PT, right? That's obtained out of similarity of the two triangles, which on cross multiplication gives us PT squared is PA into PB. PT squared is PA into PB. Right? Yes or no? So, I hope you're all fine with this. This, of course, was only a special case of the previous result. Now, again, to top it up, a property of tangents that we use very often, let me also tell you that property of tangents. If this is a circle, this is the center O of the circle, and this is a point P, an external point P from where we are drawing tangents. So from this point P, two tangents could be drawn to the circle. Let me call it PA, one of the tangents, and this is another tangent, call it PB. Two tangents drawn from P to the circle, PA, PB. These are the radii at the point of tangency. OA and OB are the radii at the point of tangency, therefore they must be perpendicular to the tangents. Yes or no? OA must be perpendicular to PA, right? And OB must be perpendicular to PB. Right? Now, look at these two triangles. Triangle PAO and triangle PBO. In these two triangles, OA equals OB. Why? They are radii of the same circle. Right? Also, OP is common to both. OP is common to both the triangles. And the two triangles are right angle triangles. This is 90 degrees, this is 90 degrees. And therefore, out of the RHS condition for congruency, right? These are two right angle triangles with two sides being equal. And therefore, out of the RHS condition for congruency, triangle PAO must be identical in all respects to triangle PBO. PAO must be identical in all respects to PBO. And therefore, if they are identical in all respects, it's then easy to suggest that PA must be equal to PB. PA must be equal to PB. Right? Which means that if I have an external point, then the length of the tangents drawn from the external point to a circle must be equal. That's an important property. Good then. Must tell you that by this time, we've been able to cover almost all the relevant properties of circles. We are ready to take on to problem solving head on. And starting with some very basic illustrations to some connected illustrations, we'll move on to advanced levels. Very shortly, I'll see you with some examples and illustrations. But this much for this time, for the sake of properties and for the sake of problem solving. This much, I'll catch you in a while. Thanks. Bye.